Humanoid robots are finally leaving science fiction behind. Today, we are seeing machines that can run, jump, dance, perform athletic movements, and even complete surprisingly complex tasks. And every new demonstration creates the same reaction. The future has arrived. But there is one problem the robot industry doesn't talk about enough. Running is not the hardest thing for a robot. Jumping isn't the hardest thing either. The real challenge is something incredibly ordinary. Plugging in a cable, picking up an unfamiliar object, opening a door, folding a piece of clothing, or simply walking into a room that the robot has never seen before. For a human, these actions require almost no conscious thought. You see a cable, reach for it, feel its position, adjust your fingers, and plug it in. Your brain is constantly processing pressure, texture, distance, resistance, balance, and movement without you even realizing it. For a robot, all of this has to be converted into data. Cameras have to understand what they're seeing. Sensors have to measure physical contact. Artificial intelligence has to decide what action to take. And then the robot has to move its body with incredible precision. That's where things become difficult, because the real world never follows the script. A robot might learn how to pick up one object perfectly, but change the shape, weight, texture, or position of that object, and suddenly the same task becomes much harder. Move the robot into a different room. Change the lighting. Put an object somewhere unexpected. Make the floor slippery. Or have a human suddenly walk in front of it. Now the robot has to improvise. And improvisation is one of the biggest unsolved problems in robotics. Humans are incredibly good at dealing with situations we've never experienced before. We don't need to be specifically trained for every possible version of a task. If we drop something, we react. If a door is heavier than expected, we push harder. If an object moves, we adjust our hand. We constantly learn from the physical world while interacting with it. Robots are still learning how to do the same thing. This is why researchers are working on something called world models. The idea is to give an AI system an internal understanding of how the physical world behaves. Instead of simply recognizing a cup, the robot needs to understand that the cup has weight, that it can fall, that it can break, that its handle can be grabbed, and that pushing it too hard could send it across the table. That sounds simple, but teaching a machine this kind of physical intuition is incredibly difficult. And there is another problem: data. AI systems can learn from enormous amounts of text and images available online. But you can't simply download the physical world. A robot needs real-world experience. It needs to touch objects, move through spaces, make mistakes, fall, recover, try again, and learn what happens when something doesn't go according to plan. That's one reason factories have become such an important testing ground for humanoid robots. Factories provide controlled environments where robots can repeatedly perform specific tasks. But even there, another question appears. Is the robot actually better than a human? A robot doesn't just need to work. It needs to be reliable. It needs to be safe. It needs to operate for long periods. And eventually, it needs to make economic sense. Because if a company spends enormous amounts of money on a robot that performs a task only slightly better than a human worker, the business case becomes much weaker. Then there's the problem of energy. Humans need food. Robots need batteries. A humanoid robot performing physical work consumes energy every time it moves its arms, walks, lifts something, or maintains its balance. And when the battery runs low, the robot has to recharge. Now imagine a factory containing thousands of humanoid robots. Some are working, some are charging, and others are waiting for maintenance. The economics suddenly become much more complicated. But none of this means the robot revolution is failing. Actually, it may mean something much more interesting. The first truly successful humanoid robots may not replace humans everywhere. They may begin with the jobs humans don't want to do: dangerous industrial work, disaster response, heavy lifting, repetitive factory tasks, working in environments that are too dangerous, too hot, too toxic, or simply too exhausting for people. And as artificial intelligence becomes better at understanding the physical world, those capabilities could expand. The real race isn't about building the robot that looks the most impressive. It isn't about making a machine that can perform one incredible demonstration. The real race is about building a robot that can enter an unpredictable environment and figure out what to do next. A robot that doesn't panic when something changes. A robot that can make a mistake and recover. A robot that can understand objects it has never seen before. A robot that can learn from experience instead of needing a programmer to tell it what to do every single time. And when that finally happens, the robot revolution will look very different from what we imagine today. It won't begin when robots can run faster than humans. It will begin when they can finally understand the messy, unpredictable physical world we live in. And when that happens, the question won't be whether robots are ready for the real world. The question will be whether we are ready for them.